Dear students, today we will discuss the physics of propagation of solar radiation from the sun to the earth. So, before I start to the physics, let us learn something about sun. So, as all of us know about sun, the sun is the largest member of the solar system. It carries about 99.68% of the total mass of the solar system, and it is a sphere of intensely hot gaseous matter, and the sun rotates its own axis about once 4 weeks. This equator takes about 27 days, polar region takes about 30 days for each rotation. If we talk about density and pressure at the center, it is tremendously high. So, in density is about 10 to the power of 5 kg per cubic meter, which is about 100 times more denser than water, and pressure at the center is about more than 1 billion atmospheric pressure. So, it is a very high pressure, and temperature at the center is estimated to be about 15000000, means it is 8 into 10 to the power of 6 to the 40 into 10 to the power of 6 Kelvin. So, it is a very high temperature, and this energy release is due to continuous fusion reaction. So, as you know how this fusion reaction takes place. So, if we consider this hydrogen atom and helium atom, if we know the mass difference delta m, so this mass of helium atom is about 0.65% lesser than hydrogen atom. So, once we know this delta m, then we can use this Einstein's famous equation, which is nothing but E is equal to delta m c square. So, c is nothing but velocity of light, which is equal to 3 into 10 to the power of 8 meter per second. So, if we substitute this delta m and c, then we can calculate the kind of energy which is generated in the sun. So, it is found that about 0.23 times radius, if we this radius of the sun. So, in this location, that means if we draw a line here and if we take 0.23 times the radius, if this is the radius and this is the r, then 90% of the energy is generated here at this core, and then this energy generated here is radiated to the outer surfaces. And as you can see, this portion is a convective zone. As you can realize, this core temperature is very high, and this surface temperature is reported to be about 6000 Kelvin. So, there is a decrease in temperature from core to the surface of the sun, and because of this, and from here it can be concluded that heat dissipation is taking place from the core to the surface of the sun, and then the amount of energy which is emitted from the surface of the sun is distributed in the solar system, and part of the energy is received by the earth surface. And if we see this energy radiation from the sun is about 3.8 into 10 to the power of 26 watt, okay, and this earth receive energy about 1.7 into 10 to the power of 18 watt, and also we know the distance between the sun and earth, it is a mean distance. So, let us see what we can learn about earth. So, this earth came into existence in about 4.6 billion years ago, Earth revolves around the Sun in an elliptic shape once per year. This Earth is inclined at 23.5 degree and rotates about its own axis. This inner core is a solid mass made of iron and nickel, and this outer core of the Earth mantle comprises solid rock. And also we know that 70% of Earth is covered by water and remaining 30% is land. And this black body temperature of Earth is about 288 Kelvin. So, we will learn why it is called black body and what is the spectrum at this temperature. So, now we will learn something about radiation. So, there are many theories available for understanding the radiation propagation, but no theories give accurate information about the radiation propagation. So, most important theories coined by two researchers. One is Maxwell's electromagnetic theory. This radiation, in this theory, radiation is treated as electromagnetic wave, and Max Planck's concept where radiation treats as photon or quanta of energy. Both the concepts utilized to describe the emission and propagation of radiation. The result obtained from electromagnetic theory used to predict radiation properties of the materials, and the results obtained from Planck's concept have been employed to predict the magnitude of radiation energy emitted by a body at a given temperature. So, these two theories are primarily utilized to understand the radiation propagation from Sun to the Earth's surface. Let us take an example on radiation heat transfer. So, here what I mean to say, how this thermal radiation is propagated. If a body temperature is more than absolute 0, then that body will start emitting thermal radiation. So, for example, if we consider an object having a temperature Th which is more than absolute 0 temperature, absolute 0, and also greater than the cold surface Tc. So, this hot object is placed in a medium, that is in vacuum, and we will show how this hot object is cooled when a cold surface is surrounded by these hot objects. So, what happens, since this hot object temperature is more than the absolute 0, it will start emitting thermal radiation, and because of this heat exchange, radiative heat exchange, so this object temperature will reduce, and only mode of heat transfer will be radiative heat transfer, because no medium is present. This is kept in vacuum. No convective heat transfer will take place, only radiation exchange will be there. So, because of that, so this object will be cooled. And same thing happens when radiation is propagated from Sun surface to the Earth surface. And from that, what we understand, we do not need any intervening medium for transferring energy from Sun to the Earth. Okay? So, this Sun will emit thermal radiation at about 6000 Kelvin, and this bulk thermal energy emitted by a body lies in wavelength between 0.1 to 100. So, most of the thermal radiation is emitted at this wavelength, is 0.1 to 100 micron. Okay? So, this micron we can represent at μm also. And if we have to learn about radiation, there are theories, but no theories give clear information about radiation propagation. So, two most important theories coined by Maxwell's and Max Planck's are utilized to understand the radiation propagation. As per the Maxwell's electromagnetic theory, radiation is treated as electromagnetic wave, and as per the concept proposed by Maxwell's, this radiation treats as photon or quanta of energy. Both the concepts are utilized to describe the emission and propagation of radiation. The result obtained from electromagnetic theory used to predict radiation properties of the material, and the results obtained from Planck's concept have been employed to predict the magnitude of radiation energy emitted by a body at a given temperature. So, what we have learned, these two theories are primarily used for understanding the radiation propagation from sun surface to the earth surface. Let us learn something about the spectrum of electromagnetic radiation. So, when the radiation is treated as electromagnetic wave, the radiation from a body at temperature T is considered at all wavelength. So, that means lambda will vary from 0 to infinity. So, we learn black body, and then how this radiation spectrum is important we will learn in the later slides. Now, our concern is, if we consider this wavelength spectrum, here what we can see, from 0.1 to 100 microns, this portion of the spectrum is known as the thermal radiation. So, most of the radiations and most of the engineering applications, this thermal radiation is applied, and also solar radiation is fall under this thermal radiation. The sun emits radiation at a temperature which is black body temperature is about 5760 Kelvin, or we can say it is close to 6000 Kelvin. So, at that temperature we get solar radiation, and that wavelength fall in the range of 0.1 to 3 microns, and under this solar radiation spectrum we will have visible range which falls in the wavelength 0.4 to 0.7 microns. And when we talk about infrared, so its range is 0.7 to 1000 microns, and in ultraviolet it is about 0.4 to 10 to the power of -2 microns. So, these informations are important because the kind of radiation what is coming from the sun, and then what happens in the earth atmosphere, and then the kind of radiation we received at the earth surface, and the radiation goes back re-radiated from the earth surface. So, these informations are required. So, short wave radiation is coming from the sun surface, and then something happens in the earth atmosphere, and then this long wave radiation which is re-radiated from the earth is like infrared radiation. So, that actually retains in the earth atmosphere. We will discuss these issues in the coming slides, and also there are informations like different kind of radiations can be applied in different applications. So, for example, X-ray, as we know, these X-ray machines are applied in many of the applications to take the image. So, each wavelength ranges from 0.01 to 100 nanometer, and of course, it is used in radiography, and for ultraviolet it ranges from 10 to 400 nanometer, and it is mostly used in water purifications, and in visible range its wavelength varies from 400 to 800 nanometer. That means 0.4 to about 0.8 micron, and this is for daytime vision and photosynthesis applications, and near infrared range for 800 nanometer to 10 microns. So, it is used for nocturnal vision, at night visions, to work at night. And thermal infrared wavelength varies from 10 micron to 1 mm, and it is mostly applied in heating and cooling applications. And microwave wavelength varies from 1 millimeter to 10 centimeter, and of course, this is used in microwave ovens. Already we know what is microwave oven, and most of the household this microwave oven is present. And radar waves, it is very long wave, 10 centimeter to 1 meter, and it is used for mobile telephone and speed detectors. And for radio waves, where wavelength is more than 1 meter. So, for use of this wave is in radio, television and communications. In this slides, we learn sun-earth relationship. So, sun is here at the center and earth is here. So, earth rotates along this path, and also earth rotates about its own axis. Sun is here, sun is also rotates about its own axis. So, this is in 24 hours, one revolution in 24 hours, and it is about 4 weeks. One revolution in 4 weeks. And distance between the center of the earth and the center of the sun is varying, because this is eccentric, this is not fixed. So, when we have to tell the distance between the sun and the earth, that is the average distance between the sun and earth. Sometimes sun earth distance is very long, and sometimes it is short. Okay? So, we must know which day is very, very close to the earth and which day is very, very far from the earth. So, this information is always known to you, and this will be more clear when we solve problems. And also, earth subtend an angle of 0.53 degree. Here this angle is 0.53, and distance between the center of the sun and center of the earth, this is the average distance, is about 4.96 into 10 to the power of 11 meter. Okay? And since we understand that because of this eccentricity of earth's orbit, the distance between the sun and earth is varies, and this variation is about plus minus 1.7%. Okay? And also one more information we must know, the angle, this is earth, and this part is equator, okay, and this is the vertical line, and this angle is 23.5. This always makes an angle of 23.5, and each rotates about its own axis. Now, we need to learn about solar constant, which is very, very important to understand why this is important in understanding solar radiation propagation. So, what is solar constant? This solar constant is defined as the radiant flux received in the extraterrestrial region of a plane of unit area kept perpendicular to the solar radiation at the mean sun earth distance. So, this value is about 1367 watt per meter square. So, this is a solar constant value, and this value will vary. Maybe if you consider in the month of June, this value will be about 1322 watt per meter square, and in December 21, if we consider, it will be about 1411 watt per meter square. This is due to the variation in distance between sun and earth at different times. So, these variations can be considered. So, this variation is about 0.33%. So, if we have to calculate the extraterrestrial region solar flux, then we need to apply this equation. IEXT is equal to ISC, which is nothing but solar constant, and then this part 1 plus 0.033 cos of 360 into n divided by 365. So, this need to be considered. So, this variation is due to the elliptic orbit of the Earth's motion around the sun. So, this need to be considered. Otherwise, this value 1367, which is the recent time this constant is used. Earlier people have made many calculations, and there are variations, like people sometimes claim that this value is 1357, okay, 57 watt per meter square, but in the recent times we use this value 1367. So, this is the precise value normally we use in our calculations. So, what my intention is in this slides, we need to consider this parameter 0.033 cos 360 n into 365 in order to calculate the extraterrestrial region for any day. So, n represent the nth day of the year. Suppose if I am interested to calculate the extraterrestrial region or extraterrestrial solar flux received on January 1, then this value of n will be n is equal to 1. Okay? So, if we substitute the value of n is equal to 1 in this expression, then what we will have, IEXT will be ISC, which is nothing but 1367 multiplied by 1 plus 0.033 cos of 360 multiplied by 1 divided by 365. Okay? Then we can do small calculations and we can calculate the amount of extraterrestrial radiation received on day 1 or January 1. So, if I am interested to calculate this IXT for say February 1, then what will be the value of n? N will be your, because January will be 31 days plus 1, this will be your 32. So, if we substitute this value 32 in n here, then we can calculate what will be the radiation flux received on February 1. Of course, this radiation is extraterrestrial radiation, which is above the Earth atmosphere. So, let me summarize these slides. What we have learned? We have learned two very important parameters. One is solar constant and second one is extraterrestrial radiation. So, extraterrestrial radiation. Okay. So, we have not yet learned what is terrestrial radiation. So, we will learn after 2-3 slides what is terrestrial radiation and what is the difference between extraterrestrial radiation and terrestrial radiation. Okay. So, this ISC will be required in many of our calculations. Okay. So, let us move to the next slides. Now, we will study how radiation is propagated from sun to the surface of the earth. So, if we draw sun here, okay, this is sun, okay, and we will have earth atmosphere here, okay, and earth is here. Okay. So, this part already, you know, I will write extraterrestrial region is ET, okay, and terrestrial region is ETR. okay, terrestrial region, and extraterrestrial region. I will write R here. Okay. So, already you know the relationship, okay, how this ISC and IXT is related, okay, extraterrestrial region, right. So, this solar radiation, so sun's surface temperature is about 6000 Kelvin, and the short wave radiation is moving through the space, okay, and we will have all the molecules here like particulate matter, and we will have oxygen, ozone, then you have H2O, this is water vapor, and maybe NO2, maybe carbon dioxide, maybe CO. Okay. So, what happens when this solar radiation is coming from the sun surface and it has to pass through this earth atmosphere. So, when this solar radiation is passing through this earth atmosphere, so the two things happens. One is absorption of solar radiation, and second one is scattering. These two phenomena will be discussed in the later slides. So, these two phenomena happens, because of that we receive a low intense solar radiation at the earth surface. So, here in these slides my concern is we need to know how this solar radiation is propagated from the sun surface to the earth surface. So, short wave radiation is coming through the space and it has to travel through this earth atmosphere. So, because and already you know this earth atmosphere is very thick, about 30 kilometer, and here what happens, as soon as it strikes the earth, so it radiates some kind of long wave radiation, Okay. So, this long wave radiation are something called infrared radiations. So, this long wave radiation reflected back from the earth surface and it retains in this earth atmosphere, and which leads to the contribution of heating up of the earth atmosphere. Okay. So, what I tried to explain here, we have sun and earth, and then short wave radiation travels from the space and then that has to pass through this earth atmosphere and it is received by the earth surface. So, some of the radiations are reflected back. These radiations they are long wave radiations and that retains in the earth atmosphere, because these are absorbed by the carbon dioxide and it retains, and this leads to the greenhouse or increase in earth atmosphere, because internal energy of this earth atmosphere is increasing, and because of that we are having temperature rise. Okay. So, next slides we will learn about solar radiation, what is terrestrial radiations, and then what is in this slides we will learn solar spectral irradiation, this is extraterrestrial and terrestrial radiation. So, it is known that approximately 99% of the earth atmosphere is contained within a distance of about 30 kilometer from the earth surface. Okay. And let us look into this figure. So, what it represents, it shows irradiance versus wavelength. Okay. So, different wavelength, what is the spectrum for extraterrestrial region and what is the spectrum for terrestrial region, right. So, this dotted line represents the solar spectrum outside the earth atmosphere, that is extraterrestrial region, and this solid line represents the solar spectrum on ground under clear atmosphere. As you can see, this region is UV this region is visible region, and then this long region is infrared region. So, this visible region is the most important for us as far as solar PV conversion or photovoltaic conversion is concerned. So, what you can see from this figure, the solar intensity is very high in case of extraterrestrial region, and this is different or it is lower in case of terrestrial region. So, what happens, why this is so? Because this radiation has to pass through this earth atmosphere. While radiation is travelling through this earth atmosphere, attenuation takes place. So, radiation what we receive, that is in attenuation form, and this attenuation is due to absorption and scattering. Okay? So, here this ozone is concentrated in a layer 10 to 30 kilometer from the earth surface, and it is strongly absorb UV rays in the wavelength of 0.2 to 0.29 micron and relatively strongly in 0.29 to 0.34 micron. So, here this scale is in nanometer, so we can convert very easily. So, this 200 means above 0.2 micron. So, 200 nanometer means 0.2 micron. So, because this is 1 nanometer is something like 10 to the power of minus 3 micron. Okay. So, that way you can understand the scale, and this oxygen absorption occur in a very narrow line centered at 0.76 micron. So, it is about here. So, these oxygens are absorbed here, and this part is ozone, and water absorption takes place in the wavelength range from 0.7 to 2.2 micron, and carbon dioxide absorbed in the wavelength more than 2.2 micron. Okay. So, this information is very important, and what we understand from this figure, the why this variation of radiation compared to extraterrestrial region. Okay. The kind of radiation we received in the earth atmosphere is different than a kind of radiation which is available above the earth atmosphere, okay, because of this absorption and scattering in the earth atmosphere. Also, we will learn what is these things like emissive power. So, this amount of radiation per unit wavelength, if we integrate it for all the spectrums, then what we will get is, it is called solar constant. Okay. So, this information will be more clear when we do some kind of numerical problems. And this is also similar curve. It shows a spectral irradiance versus wavelength. So, as you can see, wavelength UV visible wavelength range, then visible wavelength range, and infrared wavelength range. Okay. And we learn what is air mass in a couple of slides later, and which is also very important. And finally, what our concern is, like solar radiation reaching the earth surface is contained in the wavelength between 0.29 to 2.5 micron. So, this range is very important for us. See the wavelength, as we learn, the solar radiation has peak intensities in the shorter wavelength. So, when sun ray is coming from the sun surface, so what we observe at this wavelength will have peak, and then it is decreasing. Okay. So, this visible range is very important for us, and most of the solar PV is based on this visible light. And here, as we can say, when solar radiation is so this is earth atmosphere, this is earth. So, this long wave radiation is going back. Okay. So, this long wave radiation is a long wavelength radiation. Okay. The peaks will be about at 10 microns, and then it decreases. So, this is shows about long wave radiation, this is about short wave radiation. Okay. And this is at 600 Kelvin from the sun surface, and this is at earth surface, which is at 288 Kelvin. Okay. So, hot sun radiates at shorter wavelengths that carry more energy, and the fraction absorbed by the polar surface is then radiated at longer wavelength, which is shown in the figure. Now, we will discuss about the mechanism of absorption and scattering, which is very important for understanding what is diffuse radiation and what is normal radiation, because after these lectures what we are going to learn is different kind of instrument used for radiation measurement, and then how these two radiations are different and what condition we can make what kind of conversion devices. That means which radiation is important for say concentrator and which kind of radiation is important for other applications. So, we will discuss the mechanism of absorption and scattering in the slides, which is very important to understand the kind of radiation received by the earth surface and why this is so. That means what is normal radiation and what is diffuse radiation. That idea we can generate by studying these two facts, is absorption and scattering. This absorption occurs primarily due to ozone and water vapor present in the earth atmosphere, and lesser extent to the other gases and particulate matters. But scattering occurs due to all gaseous molecules as well as particulate matter present in the earth atmosphere. I will draw the same thing again here. So, this will be something like this. We will have aerosols, then particulate matters, then all the gaseous molecules, like we have O3, we have oxygen, we have H2O, we have CO, we have CO2, all the gases, and this radiation is coming, short wave radiation. Okay. So, what happens? This radiation, some of the radiation is absorbed here. So, UV is absorbed here, then at different wavelength this will be absorbed at in the different molecules. And what happens? There are some radiations which is unaffected by this earth atmosphere, and it falls directly on the earth surface, and some radiations which is diffused and it travels in all the directions and its intensity is reduced. Okay. So, the kind of radiation which is unaffected by this earth atmosphere is known as IB. IB is beam radiation or direct radiation, and the kind of radiations which is received after scattering is known as ID, it is diffuse radiation. So, if we add these two, IP plus ID is nothing but IN or IG. Okay. So, this is IG is nothing but global radiation. So, IB is beam radiation or direct radiation, beam or direct, and this is diffuse, and this is global. Okay. So, here short wave radiation is coming from the sun surface and is travel through the space, and then it has to pass through this earth atmosphere. So, while this radiation comes in contact with the earth atmosphere, so what happens? Absorption of solar radiations takes place, also scattering takes place. Okay. So, based on the wavelength, so different elements are present. So, that way they are absorbed here, like UV is absorbed in ozone layer, and then you have oxygen also absorbed in different wavelength, and then water vapor, then H2O. And some of the radiations which is strike on the aerosols, and it directions are changes, it radiated in all the directions, and some of the radiations is received on the earth surface. Sometimes what happens, there is a parameter called release scattering. So, since air molecules are present, because of this air molecules, this release scattering also takes place. So, this scattered radiations, when it receives on the earth surface, its intensity is reduced, and this reduced intensity is designated by ID, that is diffuse radiation. So, what we have learned here, we have learned the mechanism of absorption and scattering, and then we have learned the different kind of radiation, that is beam radiation, diffuse radiation, and global radiation. So, these radiations are very, very important when we do calculations related to the radiation geometries. And we need to learn black body radiations. So, for a given temperature and wavelength, no other body at same temperature can emit more radiation than a black body. So, we need to understand what is a spectral black body emission or emissive power and a Stiefel-Boltzmann constant, because we can demonstrate right now sun is a black body, or sun's surface temperature, that is close to 6000, is a black body temperature. So, we can demonstrate it. Let us start. As we know, this Planck's law of spectral emissive power, how we define it, EBW, so at certain temperature is expressed as C1 by lambda to the power of 5, and then you have E exponential of C2 by lambda t minus 1. This may be equation 1, and this C1 and C2 are constants, and C1 is something like twice pi h c square, which is equal to 3.743. Once we substitute the value of Planck's constant and value of c, it is something like 8 watt micron to the power of 4 per meter square, and C2 is Hc by K, which is equal to 1.4387 into 10 to the power of 4 micron Kelvin, and T is at absolute temperature, and lambda is in lambda is in micron, and T is this wavelength in micron, and T is in Kelvin. This is absolute temperature, absolute temperature. So, this is the spectral emissive power, and this is defined by Planck's, and also we know the Planck's law. Okay. So, this equation is 1. Now, if I am interested to calculate the emissive power, what we will do, we will integrate this Planck's constant from wavelength 0 to infinity. Let us see how we can do it. So, if I am interested about emissive power EB, that is T, this is called emissive power. earlier one it was spectral emissive power. So, if I am interested to find out this emissive power, what we will do, we will integrate this equation 1 from lambda 0 to infinity, and this equation was something like this, lambda to the power of 5, then we have exponential C2 by lambda t, then we have minus 1, okay, and this is the lambda. So, if we integrate, so I am not going to do the entire derivation. So, what I will write, what we will get here finally sigma t to the power of 4, which is watt per meter square. Okay. So, what is sigma? Sigma is Stephen-Boltzmann constant. Stephen-Boltzmann constant. Boltzmann constant, and its value is 5.67 into 10 to the power of minus 8 watt meter square Kelvin to the power of 4. Okay. So, this is a black body emissive power. So, also we can say this is a black body emissive power, emissive power. So, it is the black body radiation flux emitted from a surface at an absolute temperature T. So, in order to show the radiation emitted by the sun is essentially black body radiation, we substitute the value of solar constant. So, if we have to show that radiation emitted by the sun is essentially black body radiation, so if then what we need to do, this is equal to 1367 is equal to R by R, then we will have square sigma t to the power of 4. So, how we have calculated it? Because pi 4 pi r square is equal to, we have this is area, and then we have I as C here, and then we have 4 pi r square is the r is the radius of the sun, sigma t to the power 4. This is the distance between the sun earth. So, of course, this is a mean distance, it is a mean distance. Okay. So, that is how we can calculate. So, if we substitute the value of 1367 here, and this ISC is equal to like small r by capital R square by sigma t to the power of 4. Okay. Okay. So, if we do this calculation, then we can calculate what is T, because these values are known to us, small r and capital R, and this T will be about 5777 Kelvin. So, if we use this T and if we go back here and if we substitute this value of T here, okay, then we can calculate EB, that is spectral emissive power at different wavelength, and it is found that if we generate this EB value at different lambda, it is quite close to a black body radiation. That is why you can say the solar radiation emitted from the sun surface is a black body radiation. So, now we can solve this problem, since already we have all the data, already we have given the hint how to solve this problem. So, temperature, I mean straight away we can calculate what is T, or if we know solar constant ISC is something like R by R whole square, then we will have we will have sigma t to the power of 4, and if we substitute these values we can calculate what is t. So, students, I request you to complete this work, so that you involve how this kind of problems can be solved for better clarity. So, here we will introduce one concept called air mass. So, which is very important parameters in testing any solar flat plate collectors. We need to understand very carefully. So, most important parameters that determines the solar irradiance under clear sky condition is the distance that the sunlight has to travel through the atmosphere. Because we have atmosphere, okay, this is the atmosphere, and then suppose if we are here, so maybe sun is at our overhead, then distance travel by the sun ray is very short, and if we take here, then distance travel by the solar ray is very long. So, this angle is very important for us. So, this is maybe A, this is B, this is C. Okay. So, how we define AM is something like AB by BC. Okay. So, this is something like 1 by cos of theta. Okay. So, the distance is the shortest when the sun is at the zenith and is directly overhead, as we understand from this figure, and the ratio of an actual path travel or the path length of the sunlight to the minimal distance is known as the optical mass, what we have defined here. When the sun is at its zenith, the optical air mass is unity and the spectrum is called the air mass 1. So, theta, if theta is 0, that is 1, that is called AM will be 1 if theta is equal to 0. So, AM will be 1. So, this spectrum is known as AM1. Okay. In case of extraterrestrial radiation or extraterrestrial region, it is defined as AM0, because the radiation do not have to travel any earth atmosphere. Okay. So, because of that it is AM0, and here this figure shows the spectral irradiance variation with respect to wavelength. As you can see, this radiation at the solid line is for 6000 Kelvin black body solar radiation, and this is at AM0 in case of extraterrestrial region, and this is at AM 1.5. Why this AM 1.5 is so important? Because all the experiments, all the testings are done at AM 1.5 at an angle of 48.2 degree. So, this is very important, because solar testings are normally done at AM 1.5. We can do very small numericals. So, how to calculate this theta if we know AM is 1.5. So, if we have to do any experiment, then we have to, and that has to be validated, then we have to perform the experiments at AM 1.5 and at a solar radiation of 1000 watt per meter square. So, that is very important as far as testing of solar collector is concerned. So, we will summarize what we have learned today. So, we have learned how solar radiation is propagated from the surface of the sun to the surface of the earth, and also we have learned what is atmospheric absorption and scattering, primarily the mechanisms, how this absorption takes place, absorption solar radiation takes place, and at what wavelength that molecules are absorbed, solar radiations are absorbed by the molecules, and how scattering takes place, and because of the scattering how this radiation intensity is decreases. So, also we have understand the distinction between extraterrestrial region and terrestrial region, and also we have learned the relationship between sun, earth, and how it travels, and what is the average distance between sun and earth, and how this distance is varying with respect to the particular day, and also we have learned the radiation variation with respect to the days, and in case of extraterrestrial as well as terrestrial region. And also we have understand the different kind of radiation, what is global radiation, what is diffuse radiation, and what is normal radiations. So, when solar radiation is striking on the earth's surface without disturbing in the earth atmosphere, that is called normal radiation or direct radiation, and if it is scattered or scattered radiation is received by the earth's surface, so that is called diffuse radiation. And if we add direct radiation or normal radiation plus diffuse radiation, then it becomes global radiation. So, these are very, very primary or fundamental things we have studied today, and also finally we have studied what is air mass. So, air mass 0, air mass 1, air mass 2, air mass 1.5. Okay. So, air mass 0 means that is radiation spectrum that is received above the earth atmosphere. So, air mass 1 means when solar radiation is at the zenith, that is our overhead, and different situations may arise, but AM 1.5 is important because all the solar experiments are performed at air mass 1.5 and at an solar intensity of 1000 watt per meter square, and also this is signifies in terms of watt peaks. If we have performed these experiments at this condition, so that is the rated test, and we represent it as watt peak. So, what you can see in the modules, that is watt peak, maybe 35 watt peak. So, that represents, that is at standard test condition. So, thank you for watching this video.